Dear students, let's now discuss the grand canonical ensemble formalism of studying the thermodynamic properties of a system. So, we already have familiarized ourselves with the methodology to be adopted in the ensemble formalism while discussing the canonical ensemble formalism, and we have seen that all these formalisms are giving as same results in the thermodynamic limit, or the fluctuations can be neglected in the thermodynamic limit. So almost the same topics that we have seen in canonical ensemble formalism will be repeated here in grand canonical ensemble formalism with slight modifications of its own. So let's see how the grand canonical ensemble is different from the canonical ensemble. So while discussing the different category of ensembles, we have seen that the micro-canonical ensemble is one of the idealized state of ensemble. So in the micro-canonical ensemble, we have seen the macro state is E, V and En. E, V and N of the system. So these macro state variables are supposed to be remaining constant. So that energy is constant, the volume is constant, the number of particles is constant. And that was an idealized state of ensemble. Then a more practical type of ensemble was introduced as a canonical ensemble, in which the macro state variables were just T, V and En. So you can see that here the condition, that the constraint that the total energy should be remaining constant was relaxed, and in place of that energy was permitted to vary from 0 to infinity, or energy was permitted to fluctuate between 0 and infinity, and in place of energy the temperature of the system was assumed to be a constant. So in order to analyze the canonical ensemble method of systems, what we have done, we considered a system to be in equilibrium with an energy reservoir, right? We considered the energy exchange between a system and an energy reservoir. So the system is exchanging energy with the reservoir until both the system and the reservoir are attaining a common temperature, or we consider the thermal equilibrium between the system and the reservoir. Okay, that's well done. So in that case of canonical ensemble, the volume and the number of particles was remaining constant. Now we will see that while you come to the grand canonical ensemble, which represents what is that, open systems. So here what happens, the macro state is represented by T, V and mu. Mu is the chemical potential. So what we have done here, we have made the system boundary open for the particle exchange also to happen. So it's not only the energy which is getting exchanged between an energy reservoir, we consider that the particle number of the system is also varying. Okay, so how can we do that? We can consider that see, there is a particle reservoir also, similar to energy reservoir, where energy exchange happens between the system and the energy reservoir. Similarly, we assume that the system is placed in a particle reservoir also, where the number of particles can vary. Means the system can exchange particles with the reservoir outside. So it's another concept. Like energy reservoir, we can have a particle reservoir also. So the exchange will go on happening until a chemical equilibrium is established between the system and the particle reservoir. And you know what is the condition for chemical equilibrium? The condition for chemical equilibrium is that the chemical potential, right? The chemical potential of the system and that of the reservoir should become what? Equal. That is why you can see the grand canonical ensemble, the macro state variable mu is appearing. Mu is the chemical potential, which represents whose equality represents the condition for chemical equilibrium. So we can say that in grand canonical approach, the system is supposed to be in a state of both thermal equilibrium as well as what? The chemical equilibrium. And we'll see almost all those discussions we have done with the canonical exchange will be ensemble will be repeated here with one more additional case, that not only the energy but the particle number n is also varying. Okay, so that is a brief introduction regarding the methodology that we are going to adopt in grand canonical ensemble formalism. So let's recall that the grand canonical ensemble is a collection of the given system and a large number of its mental copies which can exchange both energy and particles with each other. So just remember, can exchange, okay, the system can exchange both energy and particles. Okay, so you can say particles, both energy and particles with the reservoir or with each other. Okay, with each other means each members of the ensemble, that's the way, which each other, right? So both E and that is both E and N are variables. So this is the thing, variables. And how long this particle and energy exchange will occur? Until, is not, the exchange will occur. This is we have to keep in mind, the exchange will continue or will occur until, what is that, the temperature and chemical potential becomes what? Constant. Okay, until the temperature and chemical potential becomes constant, means what? Until thermal and chemical equilibrium are achieved, right? Okay, so what we do is that here the system is supposed to be in contact with a thermostat. The system is supposed to be in contact with a thermostat. Thermostat, you know, means which maintains a temperature T. We usually describe it as a heat bath, right? So, and a particle reservoir that maintain a chemical potential mu. So a thermostat is supposed to maintain temperature T, and a particle reservoir is supposed to maintain a chemical potential mu, since the system is in contact with this thermostat and the particle reservoir. Therefore, as we have seen, sorry, the macro state of our system will be TV mu or mu Vt. Okay, so remember that here, so in a grand canonical ensemble, fluctuations can occur, changes can occur. So while discussing the canonical ensemble, towards the end of our discussion, we have just discussed the fluctuations in energy. Okay, here fluctuations can occur. So in grand canonical ensemble, fluctuation can occur in both energy as well as number of particles. So there be a change in the energy, fluctuation in energy as well as fluctuation in the particle number, right? So we will discuss about the particle number, fluctuations, etc. in grand canonical ensemble towards the end of our module, right? Now see, remember this particular type of ensemble formalism, especially grand canonical ensemble formalism, is best suited in studying phase changes. So the grand canonical ensemble is best suited. Each ensemble is suited for special purposes, even though the results obtained by various ensembles for the same problem will be almost the same in the thermodynamic limit. Each ensemble is regarded suitable for unique problems. So grand canonical ensemble is usually regarded as the best suit or best match, best suited for studying phase changes. So studying phase changes, you know, during phase change, number of particles can change, right? Is not okay. For example, when water evaporates, what happens is that the number of particles in the liquid state will be reducing and the number of particles in the vapor state will be increasing. Okay, so there comes the idea of chemical potential between the two phases and all. So that is to study phase changes, the best suited ensemble formalism is grand canonical ensemble formalism. Now what we'll be doing in this grand canonical ensemble formalism is this one. So let me tell you, or let me remind you what we have done in canonical ensemble. In canonical ensemble, we regarded our system to be in equilibrium with an energy reservoir, and we said that the energy of the system can vary from 0 to infinity, and by suitable methods, by two different methods, we calculated a very important quantity which is denoted as PR. Okay, what is PR? PR was the probability that the system in canonical ensemble at any instant of time is found in an energy state ER, and we obtained by different methods that PR is equal to some e raised to minus beta ER divided by Q, and this Q was equal to sum over R e raised to minus beta ER, and this Q was named as the canonical partition function. Okay, so and this equation for PR was known as the Boltzmann distribution function. Okay, so PR was the Boltzmann distribution, and okay, also known as the canonical distribution. Now see, and all the thermodynamical properties of the system was obtained by analyzing this Q. Okay, for example, we started with the A Helmholtz free energy is equal to minus KT log Q, okay, or QNVT, what we have been writing, and thereafter we got all the other thermodynamic variables. So this was the approach that we did in canonical ensemble. Now, similar to the canonical ensemble, in grand canonical ensemble also we are going to follow almost same procedure. But the major difference in grand canonical ensemble is that, okay, unlike the canonical ensemble where only energy is permitted to vary, in grand canonical ensemble both energy as well as the particle number of the system is permitted to vary. Okay, so both energy and particle number are fluctuating in the case of what? Grand canonical ensemble. So what we have to do, there will be actually double constraints. There will be two constraints. So what we are going to do is that we are going to calculate, here also probability calculation is the central theme. We are going to calculate the probability that a system in the grand canonical ensemble at any instant of time is found with an energy ES and a number of particle NR. Okay, so I'm just writing PRS. So PRS is the probability that we are going to, instead of PR in canonical ensemble, in grand canonical ensemble we will be calculating a similar quantity known as probability PR comma S. Means there are two conditions here, R and S. Okay, as well as the number of particles are fluctuating. So we have to see that at any given instant what is the probability that the system is having a particular energy and a particular number of particles. But രണ്ട് കൺസ്ട്രെയിൻസ് ഒരുമിച്ച് വരും. ഒരു നിശ്ചിത എനർജിയും ഒരു നിശ്ചിത പാർട്ടിക്കിൾ നമ്പറും ഉള്ള സ്റ്റേറ്റിൽ നമ്മുടെ സിസ്റ്റത്തെ കാണാനുള്ള സാധ്യത. Okay, so the probability, so PRS denotes, so we are just following the same notation that is used in our book for study Petria. So probability that the system, okay, any system that we are, okay, it's an open system now, in the system in grand canonical ensemble is found in a state with, in a state means in a, okay, macro state with energy ES and particle number NR. So you please note one thing, in the canonical ensemble we used the notation for energy as ER. Okay, so we used the probability PR. Now in grand canonical ensemble, what our author is using, he is using the energy value as ES instead of like E1, E2, E3. Okay, he is using ES instead of using ER. Okay, and the number of particle, okay, see, is taken as what? NR. So in place of ER he is using NR. It's just like M, N, P, Q, like that. R and S are used. Only the thing is that N is given NR as a subscript and E is given ES instead of ER. So we will be calculating PR comma S. So remember, this R is for NR and S stands for what? ES. So what is PRS in grand canonical ensemble representing? It denotes the probability that a system in grand canonical ensemble at any given instant is found in a state, okay, because the system can be in any of the large possible number of microstates, right? So we are going to find out the probability that the system in the grand canonical ensemble is found in a state with a particular energy ES and a particular particle number NR. Okay, so and that is our aim, and see, similar to the equation that we have derived here, we will be able to obtain an equation for PRS. Okay, and you will be seeing that this equation is very similar, quite similar to PRS equation. It will be looking very similar to the PRS equation, sorry, PR equation, and similar to the Q in the denominator here. There will be a quantity in the denominator for a PRS also, which will be named as the grand canonical partition function. Okay, so in order to make our study easier, I am writing that equation now. What equation we are going to write? I'm writing PRS. This is the probability equation that we are going to derive shortly. Okay, and PRS, you just look at this particular canonical ensemble equation and find out the similarity. Okay, so e raised to, there is e raised to there, e raised to minus alpha nr minus beta es. You note the difference. Okay, here only e raised to minus beta er was there, but here we are going to get an one more term as the exponential, that is e raised to minus alpha nr. So because I told you both nr and es are variable in grand canonical ensemble, divided by, okay, can you tell me, okay, can you just presume what will be the denominator? What is q equal to? So here it was q. Okay, and this q was equal to simply sum over r of e raised to minus beta er, okay, which we call the canonical partition function, or z stands sum over all states. So here the denominator quite similar to this denominator. The denominator here also is going to be sum over r e raised to minus alpha nr minus beta es. So that is the sum over r of the numerator itself. And the denominator we can call as, okay, the denominator is usually represented by you can say some z, okay, as we have seen, or it is known as the grand canonical partition function. So this is exactly what we are going to do. We will be deriving the probability equation, and this particular distribution equation will be known as the Gibbs distribution equation. Unlike or in place of what, the Boltzmann's distribution equation or canonical distribution equation, and which is relevant, is known as the grand canonical partition function, and it will be having the same role as that of the canonical partition function that we have seen here. So what is the role? The role was this Z or Q will be acting as the bridge to the thermodynamics of the system. So we will be able to calculate all the relevant thermodynamical properties of the system from the knowledge of the grand canonical partition function. So the topics are going to be one and the same. And before we end up the introductory part of the grand canonical ensemble formalism, let me tell you that there are two approaches to derive this particular equation, and this is what we are going to derive in the coming lectures. Okay, PRS equation already I have introduction, and in order to derive this particular equation, there are two standard methods. First method or first approach is by considering the equilibrium between the system. Okay, our system, whichever system we are considering, we can consider the system to be in equilibrium with a particle cum energy reservoir. Please compare this particular method with the method that we have done in canonical ensemble. So there also we have done two methods to calculate PR equation. To calculate this PR equation, I told you, we have explained methods. One was by considering the equilibrium between system and an energy reservoir. So here only one difference, one additional condition. What is that? Here we are considering the equilibrium between a system with a particle cum energy reservoir. So there is a particle reservoir also. The reservoir is acting as a reservoir for what? Both energy as well as particle, because both NR and ES are what? Variables, right? That is one approach. And after doing that, we had an alternate method. The method was known as the method of most probable distribution. Hope you remember. So that was discussed as an alternate method to derive PR equation, known as the method of most probable distribution. Okay, so where, hope you remember that we introduced two constants alpha and beta for the first time. What is this alpha and beta there? Alpha and beta were known as the Lagrange's undetermined coefficients. So by using the Lagrange's undetermined coefficient method, we calculated the most probable distribution, and from there we calculated the ratio, what is known as nr star divided by n. Okay, so in order to do that most probable distribution method, we consider the system as a member of the system, is considered to be a member of the grand canonical ensemble, and then we study what, how a given amount of energy and how a given number of particle is distributed amongst the various energy numbers, energy states, and what the particle numbers. So that is what we are going to do. So the second method is known as, or second approach is the method of most probable distribution. Method of most probable distribution. And we will be doing the calculation by using both of these methods. Most probable distribution. Okay. Lagrange's method of undetermined multipliers by taking weight factor and all. So that's about the entire chapter of grand canonical ensemble. And the good thing is that it's going to be a repetition of canonical ensemble formalism. And so the challenge is that once you understand what we have done in canonical ensemble, you can understand what we are going to do in grand canonical ensemble. And if you still have some doubts, if you are skeptic about the canonical ensemble formalism, I have a word of a suggestion that please first of all go through the corresponding topic in canonical ensemble, try to understand its methodology, and thereafter you just listen to the lecture on the corresponding topic in grand canonical ensemble. And I strongly suggest you that you should have the syllabus point with you while you learn, because we have only very limited time, and within this limited time you have to get a holistic idea of what we are actually doing in our modules, right? So it's always suggested that you should have in front of you the syllabus of, for example, module number 3, canonical ensemble and canonical ensemble. You read each of the topic in canonical ensemble under the heading canonical ensemble, and you try to find out a very similarly sounding topic in what, grand canonical ensemble. And then you listen to first the lecture once again if you have time, that of canonical ensemble, and then you listen to the lecture of the same topic in what grand canonical ensemble, so that you will be able to make a relationship, or you are able to compare and understand that there is nothing more in grand canonical ensemble except the addition of one term, that is the number of particle nr with alpha. അപ്പോൾ ഞാൻ നിങ്ങൾ പ്രത്യേകം പറയുകയാണ്, നിങ്ങൾ ഈ വീഡിയോ കാണുമ്പോൾ അല്ലെങ്കിൽ ഗ്രാൻഡ് കനോണിക്കൽ എൻസംബിൾ പഠിക്കുമ്പോൾ എപ്പോഴും ഇത് കനോണിക്കൽ എൻസംബിളിൻ്റെ ഒരു അഡീഷണൽ ഫീച്ചറും കൂടി ഉൾപ്പെടുത്തിയുള്ള ടോപ്പിക്കുകൾ മാത്രമേ ഇവിടെ വരുന്നുള്ള കാര്യം തിരിച്ചറിയുക. അതുകൊണ്ട് ഗ്രാൻഡ് കനോണിക്കൽ എൻസംബിളിലെ ഏതെങ്കിലും ഒരു ടോപ്പിക്ക് പഠിക്കുന്നതിന് മുമ്പ് നിങ്ങളെ സിലബസിൽ നിന്നും കറസ്പോണ്ടിങ് ആയിട്ടുള്ള ടോപ്പിക്ക് ഏതാണ് കനോണിക്കൽ എൻസംബിളിൽ നമ്മൾ പഠിച്ചതെന്ന് തിരിച്ചറിയുകയും അതിൻ്റെ ആ ടോപ്പിക്ക് ഒന്നും കൂടെ വായിച്ചതിന് ശേഷം അല്ലെങ്കിൽ അതിൻ്റെ കറസ്പോണ്ടിങ് ലെക്ചർ ഒന്നും കൂടെ കേട്ടതിന് വേഗം ഓടിച്ചെങ്കിലും ഒന്ന് കേട്ടതിന് ശേഷം മാത്രം എന്ത് ചെയ്യുക, ഗ്രാൻഡ് കനോണിക്കൽ എൻസംബിളിൻ്റെ ഈ ടോപ്പിക്ക് നിങ്ങൾ അതിനെ ഫോളോ ചെയ്യുന്നതായിരിക്കും എളുപ്പം. നിങ്ങളുടെ സമയം പകുതി മതിയാവും. ആൻഡ് സോ ഐ വിൽ ബി മൂവിങ് എ ബിറ്റ് ഫാസ്റ്റ് വിത്തൗട്ട് മച്ച് എക്സ്പ്ലനേഷൻസ് ആൻഡ് ഓൾ, ബിക്കോസ് മോസ്റ്റ് ഓഫ് ദ എക്സ്പ്ലനേഷൻസ് വി ഹാവ് ഡൺ while discussing what, the canonical ensemble topics. So hope that will be doing. So we'll move very fast and we will finish off the corresponding topics within no time. So be prepared. Thank you.